Okay, thank you very much. So indeed, I'm going to talk about injective types, which is joint work with Martin Escardo from the University of Birmingham. So let me just get the setting right. So we work in univalent foundations, aka homotopy type theory. And within this setting, Martin introduced injective types to construct large classes, large examples of infinite searchable types in Types Abstract from 2019. But actually, you can just study injectives sort of on their own, and they actually have an interesting theory. So that's what I want to talk about today. And I want to present in particular new examples and new counterexamples and explain why that's interesting. Okay, so let me start by giving you the definition. Should I move the Zoom window maybe? No. Yes, great. Okay, so a type D is called injective if any map into it can be extended along any embedding. So if you're given an embedding J here and you're giving a map F, then there should be a designated extension F over J such that the diagram commutes. Okay, and sometimes we say algebraically injective because we're talking about a designated extension, so it's formulated with sigma rather than the propositional truncation exists. But for the talk, I'm just going to completely drop the adjective. Okay, and just to recap, so an embedding is a homotopically well-behaved injection. More precisely, J is an embedding when this canonical map on path types is an equivalence, or alternatively, if all the fibers of J are propositions. And finally, I should say that the notion of injectivity is sensitive to universe levels. So really what you end up studying, and what we do in AGDA, for example, is that you study UV injective types where X is allowed to live in U and Y is allowed to live in V. But again, for the talk, I'm just going to skim over this completely. Okay. So what are some examples? So any univalent universe is injective. The type of propositions in the universe is injective. The type of partial elements. So that's this, this LX here, where you're taking a proposition and a map into this thing, so that will give you an element if the proposition is true. And the type of ordinals, also the type of well orderings. These are all examples of injective types. And so let me just sketch how you get the injectivity of the universe so that you get a sense of how this works. And so given a map J and a type family, now this is a map into the universe, a type family, you can define the extension by just taking the sum over the fibers. And whenever the fiber contains something, you apply F. And that's it. So this is the notation for the fiber. And this gives you a new type, right? Sigma is a type constructor, and it has the required property. And also you can use pi as well, right? So instead of summing over the fibers, you can also take a product of the fibers. Okay, and then here's some new examples. So you can also have the injectivity of the type of iterative sets and iterative multisets, which were introduced by Hakon Giltrud. So there you can take unions, right? The idea is instead of taking a dependent sum, you take unions. The types of small infinity magmas, monoids, and groups. I have a theorem for that. And the underlying set of any subcomplete poset. So in there, instead of taking dependent sums, you're taking suprema, right? And the same kind of trick applies. Okay. So how do you get the injectivity of the magmas and monoids and groups, etc.? So this is done by a general theorem that gives you a sufficient criterion for the injectivity of a sigma type. So the idea is that these mathematical structures, they're essentially, bundles. They're essentially sigma types over a universe. You take a carrier, and then you have an operation, and then the operation satisfies axioms, and so on. So you're really just building a dependent pair, and so there's a sufficient criterion that you can just apply, and then you say that the universe is injective, and therefore you just keep extending, and you keep getting injective things. So for groups, this basically turns out to be that if you have a bunch of groups, then you can equip the product of the sets of those groups with a group structure again. That's kind of the extension procedure. And for subtypes, there's actually a necessary and sufficient criterion. So this is when the type family is proposition valued. And there, it's the following. So if you have an injective type D and you have a subtype of this given by a predicate P, then this is injective precisely when you have an endomap on D called F, such that it kind of picks out the things for which P holds. So if P holds for anything in the image of F. And if P already holds for the element, then actually it's a fixed point of this map. So maybe it's a little bit mysterious, so let me give one example. So if you want, for example, the injectivity of the type of propositions, you can take P to be the predicate that something is a proposition, and the map F, which is then an endomap on the universe, is given by the propositional truncation. And this generalizes to any reflective subuniverse. And then you can check that, you know, if you truncate, then you are given a proposition, and if you are already a proposition, then the proposition is equal to its truncation, of course, using univalence. Okay, so all the examples that I've shown you so far, they're all large, like a universe, type of ordinals, etc. And that's really no coincidence. You can prove the following theorem. So here I have to be a bit careful with the universe levels again. But basically, if you have a injective type in U that is injective with things with respect, like with respect to things in U, then this type here of not stable propositions must be small. So it must have an equivalent copy in the universe U, even though like its native size is in U plus because you're summing over all of these propositions in U. So in some sense, if you want to have small injectives, you need to be impredicative, or at least you need to accept this principle. I should also mention that this not resizing, this is not provable in univalent foundations. That follows from a proof theoretic observation due to Andrew Swan. So that's quite nice. And also it ties in with a result due to Peter Axel and Benno van den Berg and two other people, that if you have the predicative set theory CZF, then it's consistent that the only injective sets are singletons. But really the kind of the paradox here, like we have examples of injectives, but also it should be consistent that there are no interesting ones. It's really just a distinction between a set and a class, right? So as soon as you allow yourself to go up, you can have examples. Okay, good. So now I want to go towards some counterexamples. So with excluded middle, the only injectives are the pointed types, because by excluded middle, you just decide the fibers and there's nothing interesting going on. Which means that the only type that is provably not injective is the empty type. But still, there are plenty of types that you cannot show to be injective. And the way this works is by reduction to a constructive taboo that already Ingo nicely illustrated. So for us, the relevant taboo is going to be not full excluded middle, but weak excluded middle. So that says that for any proposition, you can decide its negation. Yeah. So for any proposition, you're going to get either not P or not P. And that's equivalent to De Morgan's law. So let's present some examples. So if any of the following types is injective, then weak excluded middle holds. So the Booleans, the simple types, which you take by starting the natural numbers and then you iterate, you close on the function types, the type of Dedekind reals, and the type of co-natural numbers. So these are all examples that as soon as you have their injectivity, you get weak excluded middle. And that's an instance of a more general thing. Namely, if you start with any type within a partners relation and 2 points apart, and it's injective, then you get a weak excluded middle. And this apartness relation is a constructive strengthening of inequality that I don't really have time to get into. But I have more to say about it at the end. Yes, I think so, but I would have to check the fruits. I mean, sometimes you're in the situation where you need a fully excluded middle to do the converse, but I think here it's not the case. There's another kind of example that I want to highlight, which is the type of inhabited type. So this is there's kind of three types at play here. So you can look at the type of pointed type. So this is a type together with a point. You can look at the type of non-empty types, and these are both injective. But the type of inhabited types, which is a type together with an element of its propositional truncation, that's injective precisely when a very weak choice principle holds, namely that all propositions are projective, not injective, but projective. And in fact, this weak choice principle is so weak that it follows from excluded middle already. But here you can actually see the difference between double negation and propositional truncation, these different properties. Okay. So from the previous counterexample, we can sort of twist this around. We can say injective types, in particular the universe and the type of propositions, cannot have non-trivial apartness relations. Yeah, so also the type of ordinals cannot have an interesting apartness relation. And so you can see this as an internal version of a result by Zoltan Kokcis that Martin-Liv type theory does not define a non-trivial apartness relation. For that, Kokcis uses a parametricity argument, but you can kind of say really the meat of it is already injectivity. It's not nothing particular about the universe. And there's also a sort of Rice-like theorem, which says that injective types cannot have non-trivial decidable properties. So meaning that if you have a decomposition of an injective type, then weak excluded middle holds. So a decomposition of X is just a function into the Booleans, such that you have 2 points where the function takes different values. And so you can never exhibit an interesting decomposition for an injective type. So in particular, questions like, oh, is an ordinal equal to 0 or something like this will never be decidable. Any sort of statement you come up with about ordinals will not be decidable. And again, it's just a consequence of injectivity. Okay, so at the end, I would like to mention a few things for future work. So one of the types reviewers made a very nice comment about some of the closure properties of injective types possibly being an instance of more general closure properties for weak factorization systems. And so that prompted me to then look at this. And so I'm interested in seeing whether we can generalize basically the situation for types to a situation for maps. And so the idea is to have a factorization system where you have, on the one hand, you have a class of embeddings, and on the other hand, you have a class of maps that I call fiber-wise injective, which just means that you take the maps such that all of the fibers are injective types, right? So for any map, I can look at a point, I get a type, and I ask for all of these types to be injective. And then, in fact, you can prove that if you're given a square like this, you can find extensions. This is just done by extending, just like with injective types. And you can also factor maps. So any map F factors as an embedding followed by a fiber-wise injective map. So this is already in Agda, but I have to explore more this factorization system. But I just wanted to check these properties. So those are already formalized. Okay, so what's left to do? Well, really want to finish the preprint. But if you really would like to see some more, then I encourage you to look at the HTML rendering of the Agda code in type topology, and you can see all the weekly updates and whatever. And with that, I've left some time for questions. So thank you.